Entropy is a fundamental concept in physics, but it can be quite confusing. Today we'll break it down using a familiar example. Our planet Earth constantly receives energy from the sun in the form of sunlight. This sunlight is a concentrated and very usable form of energy. Plants use sunlight for photosynthesis, cars burn gasoline for fuel, and our bodies use sunlight indirectly through the food chain. But here's the key point. The Earth doesn't radiate all this energy back into space in the same form. It radiates energy back as heat, which is a lower form of energy, less concentrated and less usable. This is where entropy comes in. Entropy refers to the tendency of usable energy to spread out and become less usable over time. In simpler terms, imagine sunlight is like a tightly coiled spring, usable, and heat is like the spring becoming loose and spread out, less usable. The second law of thermodynamics states that entropy, or the measure of disorder or spread out energy, always increases over time in a closed system. Our planet and its energy exchange with the sun is a closed system in this context. Because entropy increases over time, things tend to move from a more ordered state, like a clean room, to a less ordered state, like a messy room. This explains the arrow of time, why time seems to flow in one direction, always towards increasing disorder. Entropy is a vast concept that applies throughout the universe. Understanding it helps us grasp why stars eventually burn out, why ice melts in a warm room, and why time seems to have a forward direction. A voiceover. As we move to scene 6, let's delve deeper into how entropy relates to the concept of time. The arrow of time is a philosophical concept that refers to the one-way direction or asymmetry of time, which moves from past to future. In sequence with our previous scene, imagine the split-screen view of the desk again. On one side, we see the desk in a state of complete order. Books neatly stacked, pencils upright, and a clean computer screen. This represents a low entropy state. On the other side, we see the same desk, but this time, it is in chaos. Books scattered, pencils toppled over, and a cluttered computer screen. This represents a high entropy state. Now, in a slow-motion animation, observe the transition from order to disorder. Papers gradually slide off the desk, pencils topple over, objects get dragged across the screen, creating an increasing disorder, a visual representation of entropy increase. This transition from order to chaos is a one-way street, much like time. You never see a messy room spontaneously tidy itself up. The same is true for time. We remember the past, but not the future. We grow older, not younger. This directionality of time, or its arrow, is thought to be deeply linked to entropy. So entropy doesn't only give us an understanding of energy exchange or matter disorder, it also provides a scientific explanation for the arrow of time. As entropy increases, time moves forward, and the universe evolves from order to disorder. This is the universal application of entropy, and why understanding it helps us grasp the fundamental nature of the universe and our existence within it. Text overlay. Entropy and the arrow of time, from order to disorder, past to future. Voiceover. As we journey into scene 7, let's continue our exploration of entropy, this time looking at its broader implications. From the vast expanse of the universe to the minutiae of our daily lives, entropy is at play. Picture a vibrant star shining brightly in the foreground of a sprawling space scene, galaxies swirling in the distance. This star, like our sun, began its life with an ordered structure, nuclear fusion releasing concentrated energy. However, as time passes, this fusion process generates increasing disorder within the star, eventually leading to its burnout and a less organized state. This is entropy in action on a cosmic scale. Now let's bring it closer to home. Imagine a close-up of an ice cube melting in a warm glass of water. The ice cube starts as a solid, ordered structure, but as it melts, the water molecules become more spread out and disordered. This is entropy at work in our everyday lives. Entropy explains why time seems to have a direction. We can't unscramble an egg, unmelt ice, or reignite a burnt-out star. These processes all reflect the natural tendency of the universe to move towards a state of greater disorder or higher entropy. Therefore, entropy doesn't only give us a scientific explanation for the directionality of time, but also illuminates the fundamental workings of the universe and our daily lives. Text overlay. Entropy in everyday life in the universe, from cosmic stars to melting ice cubes.